All right, so we are now in week 11, which talks about hash tables. And before I get into hash tables, before I get into hash tables, I want to jump back real quick to binary trees, since I did a beautiful notes for you in there. All right, so let's go over this stuff real quick. All right, with the deleting nodes and stuff like that. So the insert and the find and the min and the max, all that stuff was pretty, relatively easily understood, right? But some of you had questions on how to delete different things, right? So I have, uploaded this spreadsheet in there with different tabs, or what are they called? What are these called? Sheets. Different sheets for, first one is delete node with no children, right? So what is a node with no children? Well, a node with no children will be one of these two on the bottom, right? So I'm going to explore both cases. I'm going to try to delete the 7. I'm going to try to delete the 3 as well, right? So the way the delete works is we're starting, this is the delete, right? We're going to look for a key. The key we're going to look for is initially 7, right? So if we're looking for the 7, we're starting both current and parent equal to the root. The root is the 10. So initially, that's why I just pointed these orange arrows to that. And then inside my while loop, which goes on until my data of the thing that I'm at is not equal to the key. So since I'm looking for 7 and I'm at 10 initially, which is where current is, it's not equal, right? So the next thing I'm going to do in this loop is I'm going to say, all right, well, parent is equal to current, and that's why I drew this parent in there, right? So the blue parent is the one that I have made with this statement right here, and that's why I drew the arrow, right? So parent is equal to current, current was equal to the root initially, and then if my key that I'm looking for is less than the current data, right, is 7 less than 10? Yes, it is. We're going to go left. So that tells it current is equal to current left child. So the parent, after this first iteration of the loop, parent is here and current is there. So far, so good? Okay, so that's the first step. Then we're going to keep going. We're going to keep searching. So we haven't found the data. We're still looking for the 7, right? So we're at the 5. So my current from before is equal to 5. And if my key is less than the current data, which it isn't, 5 is, the key is 7, which is bigger than the current data, that means we're going to go to the right, right? So the first thing that I do in here, I say parent is equal to current. Current was the 5 before, right? So when I say parent is equal to current, I'm effectively moving the parent from here, from the top one, to the one on the bottom, right? So now this is my new parent, and then what I'm going to do is, since my key is not less than the current data, but it is greater than, we're going to go to the right, right? So current is equal to current right child. So now this is my parent, this is my current, and at that point the loop stops because the current data is equal to the key. So loop stops, right? That's what I have put in there. Okay, and then we have to delete this thing. All right, so this is the first piece of the delete function, which is if no children, simply delete it. So how do you know if it's no children? Well, both of these, so the current is 7, but there's 2 nulls connected to the bottom of it, basically, right? It has a null and a null, so that means both of these here, in this line here, both of them are equal to null, so that's true. If the current is equal to root, which it isn't, we have to figure out if it is the left child or the right child, right? One way the book does it, remember how as it goes through the search, it marks in this boolean is left child it marks to keep track of whether it went to the right child or the left child, right? Another way to do this is, instead of saying is left child here, you can say, and actually it's the right child. So since the last time we went through this loop is left child is equal to false, that means we're going to go into this else here, which means that it's the right child. Another way to do this is, instead of saying is if, else if is left child, I could say else if current is equal to the parent left child. Does that make sense? So this is my, remember, in here, when you're looking at when you're looking at this here on the top, right? This is your parent, right? This here, the one on the left, the 3 is the parent left child. The one on the right is your parent right child, right? So in other words, I can add a little text box in there. Where's my text box? All right, and here I can say this is my parent right child, right? So if I say if current is equal to the parent right child, which it is, that will be another way to do this line right here. So instead of using the is left child as a marker to indicate where I'm at, whether I'm in the left or the right child of the parent, I can just use the parent itself. But anyway, so we're in the right child of the parent, so that means that I'm going to say, all right, well then make the parent's right child equal to no. In other words, we're going to change the 7 from up here to, we'll just turn into a no. And that's it. No, delete it. Okay, now let's do another way. Now we're going to do the same thing for deleting the 3. And the searching goes the same way. So we're going to go initially, the parent is the root, then the current is the one under it. Then we keep going. Since the data you're looking for, the 3 is to the left of current, right? Current was here, right? We're going to go to the left one. So now current is the left child of the parent, which is, now we're falling into this right here. The else if is left child. Parent left child is equal to no, right? And again, I could have replaced this else if, instead of else if is left child, I could say else if current equals parent left child. Does that make sense? Richard?
Yeah, but it seems like it kind of makes it more confusing. It's simpler
right.
in this format.
Well, okay, if you find it simpler, that's fine, but I'm just telling you that there's another way to do it.
Right.
So, okay, so then this way is now we're telling, okay, the parent left child is equal to no. Okay? And then there's another case for this, which is the if current is equal to root. So since I'm exhausting all the possible options, let's look at that. So let's say, suppose you have only one node, and that's the root, and it doesn't have any children, right? So in that case, we're not going to look through the loop at all. We're not going to search at all, since the current data is equal to the key. Loop doesn't happen at all. And then the only thing that we're going to do is we're going to tell it, if the current is equal to the root, then make the root equal to null. So that just turns the root into null, and that's it. Okay, so that exhausts all the different possibilities for when you have no children, right? A node with no children. Okay, so now the next one is delete a node with one child. Okay, so that one's not too bad either. So let's say we have, we just have this situation, right? I have a 71 and a 63 and then a null here, right? So the first initially, let's say I'm trying to delete 71 when the node to delete is the root and has a left child, right? So I'm starting with that case. So I'm deleting 71, 71 is the root, and 71 has only one child, which is the 63, only left child. Okay? So again, we're not going to go through the search at all. We're not going to go through this because they're not both of the children are null. So now we're going to go when the current right child is equal to null, right? And again, this is my current is the root, the right child is equal to null, so that's this case. Okay, so if that is the case, and it's the root, we're going to say the root is equal to the current dot left child. So this is the current left child, this is my root, and I'm just telling it, okay, we'll move the 63 up to the top. Root is equal to that thing. So this is what happens. Root is equal to the current left child. Make sense? Okay, next one is trying to delete 71 when it's at the root, but then this time it only has a right child. So we have a null connected to the left. Okay, Same deal as before. We go through the loop, nothing in it. We're not going to do anything in the loop. We're ignoring this piece. We're not going to look at this part here because now the current left child is equal to the no, which is what we have. Okay, so if the current left child is equal to the no, which is what we have here, and my current is equal to the root, right? Parent and current, they're all equal to the root, which is that's the case. Then I'm going to say root is equal to the current right child. This is the current right child, right? To the right of the root. So I'm just telling it, root, you're equal to that. So the 73 goes all the way to the top. Okay, and what happens to the old node? Java Virtual Machine clears it up with the garbage collection. Since nothing refers to the 73 after the deletion, it just gets wiped out eventually. Okay, so that was if it's the root. So I basically handled both cases, which is the one right here when it's the root and it's the left child that is equal to no, and also handled if it's the root and the right child is equal to no, which was the next one. Okay, so both of these are handled. So now the next one is we're going to do delete 71 when the node to delete is the right child and it has a left child, right? So here's the situation. I have this binary tree in there, and to create these, I just use the the little visualize binary tree link that I have on the class page, right? These one of these here, okay? To make my binary trees. Anyway. So I have an 80 on top, then I have 52, then I have 48, 71, 63, 67. That's the arrangement, right? So I'm going after the 71. And so what can we say about the 71? It itself is a right child, and it has a left child, right? So let's work our way through this. So first, initially, just like before, I'm starting the current and the parent equal to the top, which is this arrangement right here, right? Parent is equal to current is equal to the root. That's the first one. Okay. Then I start looking for 71. First time I go through the loop, parent is equal to current. So that's this arrow right here. So parent is equal to the root. And then current is equal to the current left child since my 71 is less than 80, right? So now we're moving current here and we're creating parent here. So parent and current are this way. So now we're going to go through the loop again. Okay, so again, I just redrew the whole picture. The ones in orange are the old ones, right? So this is what we had from before, right? The parent is all the way on the top, and the current is the 52. So I just redrew them here, but in orange this time, okay? So now I'm saying parent is equal to the current. So basically the blue here is equal to the orange. So my parent now is here, okay? And then if my key is less than the current data, it isn't. Since 71 is bigger than 52, we're going to go into the else. So I'm going to say, all right, now current is equal to the current right child. In other words, the current moves right here to the right child of the old current. Okay? And at this point now, my current data is equal to the key because I was looking for 71, and this is where we stop. Okay? We're not going to go through this since this is my, if we have no children. And we're going to go to if my current right child is equal to the no. Current right child is equal to the no, right? That's my current. That's the current right child. It is equal to no. And it is in the root. I already handled the root case in the first two examples that I showed you. So now we need to look at, is this the left child of the current or the right child of the current? Well, it is... is the current the left child of the parent or the right child of the parent? Well, the current is equal to the right child of the parent, right? See how now it may be a little bit easier to visualize instead of the is left child. So in other words, we're going into the else, right? So current is the right child of the parent, which means we're going to say the parent right child is equal to my current left child. In other words, this one becomes equal to this one, right? And what we're going to do is we're just going to get rid of the 71 and we're going to shift the 63 all the way to the top, or the place of the 71. So that's that. So far so good? Okay. So now we're going to do another one. Now this time is delete 71. The note to delete is a right child, and it has a right child. Right? So now what we're going to do is I have this arrangement where this is my parent, right? This is my current, and it's the same search algorithm, right? The parent and the current are still going to stop at the same place for that same binary tree, right? This is my parent right child. This is my current. This is my current right child. This is my current left child. Okay, so since my current left child is equal to no, which it is right here, and it is in the root, right? And the current is equal to the parent right child. That means we're going to go into the else here, and we're going to say the parent right child is equal to the current right child, right? So in other words, this right here is equal to this right here, right? Parent right child is equal to the current right child. And in other words, what we're doing is we're just grabbing the 73 and we're connecting it right where the 71 was. Okay, parent right child is equal to the current right child, and we end up with this picture right here. So far, so good? Okay, so that's that one. Now,
What happened to the current left child?
current left child is no. It's nothing. It doesn't exist. It never existed in the first place. It's just no. Yeah. So we don't worry about it. Okay. So all we really care about is the 73 and the 72. We just have to reconnect the 73 back to this point right here. So remember that we don't have to, since the 73 might have a whole bunch of nodes linked underneath it. We don't care about all the other nodes that are linked underneath it. All we got to tell it is, okay, you, the one on top, connects to the one on the bottom, and then all the other connections underneath in the subtree are already still there, so we don't have to remove connections or anything. Okay, so that's that. Now the next case is delete 71. The note to delete is a left child and has a left child. So now I had to redraw a different tree. So now I have a 90 at the top, 82 at the bottom, 71 is the one that I'm going for, and the 71 has a right child of no and a left child of some data. All right? So in other words, this is my parent, and the search kind of works the same way as before, right? This is my parent, the current is the one underneath it, which is actually so current is equal to my parent left child, and then what do? So current right child is equal to no, which it is, right? And the current is equal to the parent left child, which is this case right here, right? So then I have to say parent left child is equal to current left child. In other words, this here becomes equal to this here, and we just shift the 63 and 64 right to the place where the 71 was, and that's it. Deletion done.
Yes, I just want to zoom out a little bit. I want to see the difference between those two patterns.
Mm-hmm.
So we're moving the 71.
So yeah, we're just grabbing the 63 and the 63 and 64, those two nodes, and we just shift them up. We just basically just connect. What we're actually really doing is we're saying, parent, your left child is no longer the 71. Reconnect yourself all the way down to the 63.
Scroll down, please. Thank you.
Yep. Okay, so again, well, all we're telling it is we're telling 82, your left child is no longer equal to the 71, it's equal to 71's left child. Okay, so that's that one. Then we have another arrangement when the note to delete is a left child, still as the same as before, and it has a right child. In other words, there's a right child here and there's a left child of no. Okay? So now this is the last case basically. So now if current left child is equal to no, which it is, right? That's what we have here. And it is the left child. It is current is the parent's left child. Then what we're going to do is we're going to say the parent left child is equal to the current right child. In other words, I'm telling it, parent, your 82 are no longer connected to the 71. You're now connected to the 73. Okay? And now this is the new connection that's established in there. Okay? So those are all the possible cases that you can have when you're deleting a node with only one child. Okay? And you already saw the deleting with node with no children. That was the easiest one. And now this is the most difficult of all of them, which is trying to delete a node with 2 children. Okay? So, and by the way, there's a couple of ways for you to delete a node, right? So the way we're going to delete a node that has 2 children is, let's say we're deleting this 12, right? Is that what we're going after? Yeah. So let's say, let's go through this thing the same way as before. So initially, current and parent is equal to the root. So that's my parent. I say parent is equal to current. So parent is here, current is there. Current. So is my key less than the current data? Well, I'm looking for 12, which is greater than the current data. So I got to go into my else. So that's going to make current is equal to the current right child, which is how we end up with the current being there. Yes?
Question.
What's up?
I look right up there at the top, and for some reason I'm tripping over Boolean. Is left child equals true?
Yeah, it's just by
It's not the left child, it's the right child.
Don't look at this Boolean here. Don't look at the one here. Look at the one here. This is
But
this.
how do we get to that point? If it's
Well,
true,
you're gonna go into the loop and get to that.
But if it's not true, how do we get it?
No, it is true. So the first time, okay, look. So we're looking for 12, right?
Right.
Okay, is 10 equal to 12? No, it isn't. So that loop is going to happen. Right? Since we haven't found the data yet, 10 is not equal to 12. We're going to go into the loop. We're going to make parent equal to the current, which is initially equal to the root. And then since the data that I'm looking for, which is 12, is not less than my data, so key is not less than the current data, that means we're going to go into this else right here. And we're going to say current is equal to current right child, and that's where we're changing the is left child to equal to false. All right, so yeah, we're going to change it. We're going to get into the loop and we're changing it. Okay? But anyway, this is my arrangement. I have parent is here, I have current is here, and my current is actually equal to the, or another way to call it what it is that's what I was saying, that it's actually easier to me to kind of say, all right, well, this is also, another name for current is the parent dot right child. Yes?
Yeah.
Okay. So there you go. So now current and the right child, so it is the right child. All right, so we're stopped there. So now we're going through these different ones, right? So again, we're not going to go through this because this one was for no children. We're not going to go through these two, which was for if you only have one child. So now we're getting into the else. And what we're going to have to do is let's examine how we're going to be going through this thing. So the way we're going to go through this tree is we're going to start at my current, and first we're going to go to the right, right? We're going to make a right, and then we're going to go make a left, and then we're going to keep trying to make left, left, left until we hit a no. Right, so first I started at my current, right? I started my current, I make a right. The first one I make a right. So right after my current, I'm going to make a right. Then I'm going to keep trying to make lefts until I hit a no, right? So, and I just simplified it. I didn't want to add an extra one, so there you go. We hit the no right away. So this is my current. We make a right, then we make a left, and we hit a no, right? There's no more lefts to make, so we stop at the 12th. Okay, and this is going to be my successor. Okay, so the next thing that I'm going to do is, I'm going to grab my successor. The 20 is going to be my successor, and I'm going to move it to the place of the 12th. Okay, and the next thing that I'm going to do is, I'm going to grab these two. I'm going to grab these two here, right? And then I'm going to connect them. I'm going to connect these two to basically this one right here. So the 20 moves up to the top. The 38 gets connected to these to the two children of the 20. Damn it. Come on, work with me. So I'm going to reconnect these two children to the 38 right here. The 20 is going to get moved to the top. And then the next thing that I'm going to do is I'm going to have to do some more connections. But that's the idea. Okay, so I find the successor. Huh?
Is that because the 12 or the 20 is greater than the 12?
The 20
but
is...
But it's less than the 38? Is that why?
The 20 is the next biggest number after the 12. Does that make sense? On the right subtree. Does that make sense?
Yeah.
So that's how we find the successor. The successor, which is the 20, is the biggest node of the right subtree. And there's another way to delete this, by the way. So this is, you can also grab the biggest node of the right subtree, or, you know, basically the next highest node, or this is actually the smallest node of the right subtree.
But then the part that I'm wondering what happens is now you don't have a binary if you still have 12 attached to 38. So 12 is...
No, 12, you'll see. We'll get to that. I'll step through all the steps. You'll see it. But I just want you to know that this is what's happening. We're going to go the path that we're going to take to find the successor. So the successor in this particular algorithm is we're looking for the next biggest node after 12 in the right subtree. I could also tell it go in the left subtree and then find, so 20 here. If I look at, come on, click it. If I look at this subtree right here, right? This subtree here, the smallest number in that subtree is the 20, right? If I was to tell it to go to the other subtree right here, the one on the left, there's a way to do that too. In fact, in the visualized links that you have in there, they're using it that way. So the way they're doing is they're telling it, okay, go in the left tree and look for the highest node in the left subtree. So there's two different ways to delete a key and shift things around. One is if you use the smallest key in the right subtree. The other way is to use the largest key in the left subtree. I'm only going to show you how to do it how to do it this way, and you can draw it for the other ones if you want. Okay? So, all right. No, the program just does this way. No, the program just does the one I'm showing you. So we're going to go, the program starts at current, and then makes a right, and then keeps going left until it stops at a null, and that finds it the successor, and the successor in the right subtree is the smallest node after 12. Okay? Or the next largest number after 12 is the 20. That's the successor. Okay. So anyway, that's the idea that we're going to do. So now let's see how it works. So first, we're going to,
real quick,
yeah.
Go ahead back to the drawing.
Yep.
So then this here gets connected here.
No.
And this jumps underneath here.
No. This is going to get connected to this one. So we're going to get rid of the 20. The 20 is not going to be, we're going to grab the 24 and the 27, and we're going to connect it to the 38. The 20 is going to get moved to the place of the 12, and then we're going to do a couple more connections. But you're going to see that as I'm moving through the successor business.
Yeah, this is when it gets fun.
There's no way you can imagine this in your head. You have to draw it. Yeah, just
Two ways you can get the minimum on your
Right.
side or the maximum
on the left. Yes.
Three, that's left.
Yes.
Okay.
So there's two different. So that you could pick a. You could also. So there's two different ways. So you could grab the 11 and put it in the place of the 12, and then you're done. Right? That will basically tell it. Now you're telling, okay, go to the right, to the left subtree and find the biggest node. Well, there's only one of them, and then move it all the way up to the top. Or the other way is what we're going to deal with. Okay. And by the way, if you build this tree in the visualize tree thing, and you try to delete 12, it will try to move the 11 to the place of the 12 because it's going the other way. Okay? So it's not going the path that we're going to go in our program. But anyway, so now the first thing that I'm going to do is, so now we know that we didn't go through any of these other ones in here, right? It doesn't have 0 children, it doesn't have 1 child, it has 2 children. So first we're going to have to find a successor, and then what's the successor? Returns the node with the next highest value after del node. So it goes to the right child and then right child's left descendants. So it goes again. It goes right and then left, 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 left. All right, so let's examine this thing. So I am inside my get successor method, and let's start the madness right here. So first of all, remember that I have already found what I'm trying to delete, right? So I have found my parent and I have my current, right? Current is what I'm going to be deleting. Okay, so in here I'm saying node successor get successor current. So that means that the del node here, the del node parameter in my get successor method is equal to the current, right? So del node and current are still, we're talking about the 12th, okay? So now that we go into the del node and we know that, we're saying successor parent is equal to del node, successor is equal to del node. So those are these first 2 orange arrows, right? So del node is equal to the successor parent, which is equal to the successor itself, right? So that's these 2 lines, the first 2 lines that we have in here. The next one is current is equal to the del node right child, and that's the first right turn that we're making. So we're telling, okay, start from the current and go to the next right child. So now it's going to go current is equal to the 38, right? So now basically that's what we did here with the last orange arrow, right? We said current is equal to del node right child. This is my del node, right? And the del node right child is what current is equal to now. So this is my current here, right? This is my del node. That's where we are at before we get into the loop. Okay, now we're going into the loop. Is current equal to no? Well, no, it isn't. Current is equal to 38 here. Okay, all right, so we go into the loop. Successor parent is equal to successor. So the successor parent is what I have in black, right? Which is equal to the successor, and the successor was what I had as orange right here. So in other words, successor parent is equal to the 12. Then the next step is I'm saying successor is equal to the current. Current was here, so successor is equal to this one now. So successor parent is 12, successor is 38, and my current is equal to the current left child. Why do I go left child? It's going to keep going to the left, left, left until it reaches a no. So now my current is 20, successor is 38, successor parent is 12. Okay? And it's not equal to no yet, right? And successor is not equal to the del node right child. We'll talk about this in a second, but basically what this piece tells it basically is, if you get to successor right here, if you get to the 38 and whatever's after it, if this successor here happens to be the del node right child, then all you got to do is grab the 38, 72, and 90 and then shift them up, right? But we're not going to do that, right? That's the simpler case, okay? So the next thing is, let's go to the next one. So, all right. So this is the arrangement that we had in here. Now we're going to go down one, okay? So now it keeps going. All right. So the first line here, successor parent is equal to successor, right? So in blue are my old ones, right? So this was my successor parent, this was my successor, this was my current. Okay, so this first line here tells it successor parent is equal to successor. So that means successor parent is now being moved here. The next line, I'm telling it successor is equal to current, which is now this black successor is equal to the old current. And then I have to tell it current is equal to the current left child, which is now equal to no. Okay, so at this point now the loop stops. Okay, so the loop stops at this point, and then we're going to go look at the if, but that's the next one. So, so the successor is not equal to the del node right child, right? If it was equal, if they are equal, in other words, if my successor here is actually this one, then I don't even need to make any new connections or whatever. All I got to do is I have to say, all right, well, this is the successor connected up there where the 12 used to be, and that's it. Okay? Well, actually, there's a couple of connections. I have to tell it, connect this 38, the left child of the 38 needs to be the 11, and the right child of the 10 needs to be the 38. So there's two connections that I need to do, and that happens after I return the successor. Okay, but we're not going to look at that. That's not the case because my successor is not equal to the del node right child. Right? You can see that that's not the case. All right. So that means that now we're going to go into the if here. Right? We're going to go into the if, and we're going to have to establish some of these connections. And to me, this was the hardest part to visualize. Okay. So here's what happens. So now that we have landed this thing to, this is the big picture, right? This is where it goes. Okay. So now, let me zoom out a little bit so maybe we can see the whole thing. Yeah, good enough. All right, so the first one is successor parent left child is equal to the successor right child. Successor parent left child is this. If I can click it. Come on. There you go. Successor parent left child is this. I'm telling it, you are equal to the successor right child. In other words, I'm actually telling successor, your left child is no longer the 20, your left child is now the 24, which establishes this connection here, right? The 20 is still there, it's floating around in memory, right? We haven't abandoned it just yet, so that's why I left it here, right? So the successor is still there, successor right child is still here, and then you still have the node to the left of that thing, and then the 27. So this arrangement here still exists. Right, the arrangement above this thing that I'm highlighting, right? Okay, so the first step was connect the 38 to this successor right child. Okay, so far so good? All right, so now the next step is I'm going to say successor right child is equal to the del node right child. Okay, so this was my arrangement with the successor, right? So successor right child. Okay, so when I say successor right child, right? Successor right child, I can't highlight it in there, but whatever. All right, so successor right child is equal to the net node, and it hides the whole thing, but there's a del node right child. Let me try to maybe move it. There you go. Okay, so successor right child is equal to del node right child. Where's my del node right child? It's right here. Right? So in other words, I'm telling it, okay, you successor, your right child is now going to be the 38 up here. So I'm grabbing this 38 here, right? I'm grabbing this 387290 subtree, and I'm connecting it where the successor right child used to be. Okay? And I have already established this connection here. I have already told the 38, your left child is going to be the 24 and 27. So we already have that in there, right? So now what we have really done is we have established a connection between the 38 and the 24 and 27, and we have also established a connection between the successor and the 38 subtree. So far, so good? Okay, so now what we're going to do is now that we have reestablished, now that we have established these new connections, now we go back to where I was called, right? So now I'm going to return the successor, which basically returns this whole thing here with this arrangement, right? So I'm returning that whole thing up to back to where it started. So node successor is equal to that thing, right? All right. So if the current is equal to the root, it isn't, right? And it is a left child. So again, let's go back to this here. It is not a left child, right? Because we have, this is my delete node, right? And the delete node is the right child of, wait, hold on. If it's left child, so if, now I'm getting confused. So if it is a left child, parent of current to successor. So parent to successor. Where's the parent? I think this is the parent. Wait, I have another picture in there somewhere. There it is. Okay, here we go. That's why you need a million pictures to see this thing. Okay, so this is my parent, right? This is my current, which is also the current right child, right? So in other words, this thing is not the left child here. So current is not the left child of the parent. Current is the right child of the parent, which is why we're going to go this way, right? So we're going to go parent right child is equal to successor. In other words, I am now going to tell it, okay, parent, you are now connected to this thing that I brought back, which is basically I'm establishing this connection here with the blue circle that I made. So I have connected the 10 to the 20, right? And the 20 itself has this kind of an arrangement. Okay? So then what, actually, no, this one actually had this kind of an arrangement, right? So the 20 originally is actually connected to a null. Okay? So I'm going to have to replace that null with the 11, right? So I'm going to have to bring the 11 back into the picture. So then I go in here, and that's the next one. So successor left child is equal to the current left child. In other words, I'm establishing this connection here. I'm telling it, okay, 20, you're now connected to the 11. Okay? Or if you want to visualize it with like that little subtree picture that I had from above, I'm changing this thing here that I had. I'm changing it so that now instead of a null, I have an 11 here. Right? And that's pretty much it. And now we have deleted it.
So the successor will always come back with that null spot.
The successor will come back where it was, yeah, where the old one was, and then you have to reestablish this new connection here with whatever's left in there, the 11. Okay? So there you go. That is how you delete from a tree in every way possible. Actually, I didn't do every way possible. Now, you can also, play around when, if it's a root or if it is not the right child. But, I'm not going to draw every single one.
What I'd like to do is review this, and then next week come back to you and explain it to you.
Sure. Sounds good.
That's what I'd like to do.
Yeah,
If
sounds
I can
good.
explain it to you, then I've got it.
Yeah, sounds good. But really, the best way to really understand it is just do what I did. Just start all the way at the top, and then break this thing line by line, draw some pictures in there, and that's really the way to do it. And it's the same thing that I'm trying to do for that merge sort. But actually, the merge sort turns out to be even more challenging than that thing. Just let me show you what kind of a thing I'm dealing with the merge sort. So I kind of started with a really big array, but whatever. So yeah, so if you really wanted to visualize the merge sort, you're gonna have to do this kind of a stuff in here, right? So I start with the merge sort, then I go into the recursive merge sort, then it calls itself with these two sets of numbers, then it goes into this, what are the values for these numbers here, then it calls itself again, and it keeps calling itself and calling itself and calling itself, until at some point it can't call itself anymore, and then it starts coming back and starts coming back, then at some point it's gonna have to merge things, right? So you really have to kind of, you can't do this in your head, okay? You have to draw it out, and even, don't even try doing it on paper or anything. I think Excel is the best for this kind of stuff, unless you're really smart and you can do it on paper, maybe with smaller sets of arrays, okay? But I just figured it would be really cool if I did a bigger array. Maybe 9 shouldn't have been the number I chose. I should have gone with like 7 or something, but whatever, okay? It's a fun little game. So anyway, so that's how you do these. That's what I would recommend. And if it looks confusing in the beginning, that's okay. Just take your time, go through it, just draw it out step by step. If you get stuck on something and it doesn't make sense, take a little break, walk around, get some fresh air, then come back to it. Maybe take a nap and then come back to it again. And after a few naps later, it will click, it will become clear. Okay, hopefully. So anyway, that is basically the trees business. Now let's go back, or let's go forward to the next chapter, which talks about hash tables. Okay, so hash tables. What do I have for hash tables here? Let's see what I have for this lecture. Oh, there's a dictionaries. Oh, I have a long video from Berkeley, where this super nerdy guy explains hash tables in Berkeley language. So if you want to confuse yourself, go ahead and watch the video. But it's also a good taste for you to see what kind of a thing they're putting you through, and if you go to Berkeley and take this class. Okay. So anyway, I'm not going to write anything on the board. I don't do that. So let's watch the video if you want to do this. And then you can look at CS61B and Berkeley. Let's just do 61B.
Can you look at that document that you just went over?
Which one?
The one that
This here?
the binary tree explanation of the deletion function?
This here?
Oh, yeah, that.
What's up?
Oh, I'm sorry, can we have access?
Yo, you have it. I have posted this already. So this is posted. This is posted in the previous week. That's where I downloaded it right now. It's this link right here, the videos. I mean the notes.
Okay.
Yeah, if you click on the notes, you got my masterpiece. It's all in there. And enjoy. You can frame it, put it on the wall or something.
All right, thank you.
Yeah. So, okay. So anyway, this is the Berkeley's webpage for what they teach in their data structures class, I think. All right. So, yeah, I guess I'm not feeling too bad about myself. All right. So look, on week 10 they're talking about hash tables, and we're talking about this in week 11. So hey, we're kind of following Berkeley's style. So anyway, going back to week 11, hash tables. All right. So first of all, some languages, and Java is one of them, has there's arrays, there's vectors, there's array lists, there's dictionaries also. Okay, and if you've taken Python and you've done a dictionary, you have an idea of what a dictionary is. Okay, in fact, it might be, I don't know if I want to go to my Python webpage to show you what a dictionary looks like, but I might. All right, and if you haven't taken my Python class, you should, because I got some dictionaries in there. Okay, so a dictionary in Python, and don't worry, Python syntax is very easy to follow. So in a regular array, right? Let's look at this thing on the bottom, right? This is the Python system out print line. All right. So in a regular array, inside of the square brackets, you put numbers, right? That's the index. Okay. Well, in dictionaries, instead of numbers, you put words. So these words will translate to a specific element in the array, right? So you can basically have a list. This is my dictionary, right? In here, I'm telling you, okay, well, this index here is going to translate to this. This other index here is going to translate to something else. So in other words, in Pythonish language, when I do this, I have created a dictionary of two things. This first one, if I type 2 in the dictionary, then it will show me the actual translation for that word, etc., etc., etc. So this is the kind of thing that we're going to be doing with our dictionaries in the hash. This is the idea behind the hash tables, or this is how we come to the dictionaries using hashing. Okay, so looking at hash table, all right, and this is straight out of the book, all right. So hide sidebar. Okay, so the whole thing here is basically they tell you, all right, so let's say we're trying to come up with some kind of an array that is going to hold the English language, and we want to have like a unique identifier index for each of the words that we're trying to map on for our dictionary, and we can come up with some kind of a scheme where each letter is equal to some kind of a number, right? Like A is equal to 1, and the Z is equal to 26. So if you have some kind of a word like cats, then the C is going to be 27. And it depends on where it is, right? So if it's the first one, right? The S here is equal to 27, which is what the S is. Right? No, it's not 27. It's a power of 27. Right, hold on. Base of the words will be 7. Oh no, that's how many letters you have. Right, so it's the 27 to the power of 0, that's my S. Then the T is to 27 to the power of 1, then this is that. Actually, and then you're replacing each of these, right? The C is a 3, right? And then the A is a 1, and then et cetera, et cetera, et cetera. So in other words, if I wanted to map this thing, then I would have this kind of a number, 6,337. That would be the index for my word cats. Okay? All right. So now the problem with this is that if you are following the scheme for a 10-letter word, you would end up with this kind of a giant number. Okay? And you can't really make an arrays this big. All right, you're going to run out of memory. Okay, you're gonna have a nice little crash if it's whatever language. Okay, so what we need to do is we need to have a way to compress this huge range of numbers to kind of have them shrink into maybe an array of 50,000 or something like that. Okay. So what we're going to do is we're going to do hashing. So how does that work? Well, this works like if you remember, let me throw that in there. Let me make a new one real quick. Oops, not that class. Let's do it in 27. New class, and I'll call this hashing. Okay. Just to illustrate to you what's happening and how it happens. All right, so let's say you have a system out println, and then I have 10. Well, let's do 7 modulus 3 equals plus 7 modulus 3. Okay, you remember how the modulus operator works? How does it work?
It's just the remainder.
Okay, so what's the remainder here?
2.
Are you sure?
Maybe not.
Maybe not. All right, let's check. So the question is basically how many times does 3 fit into 7? 2 times. 2 times, right? So 7 minus 2 times 3 is equal to 7 minus 6 is equal to 1. So it's 1, right? So this one shows you 1. Okay? So now let me grab this thing here, and I'm going to change it to 6 modulus 3. What's my remainder now? 0. Okay? So it's the same question again. How many times does 3 fit into 6? Right? And it's 2 times. So 6 minus 2 times 3 is 6 minus 6, which is 0. That's how we get the 0. Okay? Let's do 5. Right? I'm going to grab this whole thing here. All right, let's do 5. 5 modulus 3. What's that now? Okay, how many times does 3 fit into 5? 2 times. No, 1 time. 1 time, right? So 5 minus 1 times 3 is 5 minus 3, which is 2, right? And if I go to 4, let me copy this whole thing. Okay, so what is it if I do a 4? What is it now? 1. Okay, what if I do, wait, I forgot to update that. That's a 2. What if I do an 8? If I do an 8 modulus 3, what is it now? How many times does 3 fit into 8? The remainder is 2, right? So 3 fits 2 times into 8. So 8 minus 2 times 3 is 8 minus 6, which is how you get the 2. Okay, so you notice something in here? Like what if I said, all right, I had some kind of a int random num, and you don't know what that number is, right? Something like that. And then I do, okay, system out, and I have this random num, And again, you don't know what it is, right? So maybe I should just, yeah, okay. So you don't know, you really don't know what the number is. So imagine you're not even seeing it. What do you anticipate this number modulus 3 to be equal to?
Something in the range of 0 to 2.
0, 1, or 2, right? Those are the only possible values that we can have when you do a modulus 3. Well, guess what? That's exactly what hashing is. Okay? So when you get a big number and you do the modulus thing to that number, you're actually reducing it in groups of smaller numbers depending on what the right side of the modulus operator is. Right? So if it's 3, it's 3 numbers from 0 to 2. If it's 10, it's 10 numbers from 0 to 9, etc., etc., etc. Okay? So that's exactly what we're going to do in here. All right? We're going to get a really big number, and we're going to do so a large number, modulus, smaller range of numbers, and that is what's going to give me my actual hash. Okay? But there's some issues, right? As you saw in the little demonstration that I did here, there's many different numbers that will map into a 2. And there's many numbers that will map into 1, and there's many numbers that will map into zeros. Okay? So that's the issue that happens when you get a big number of, a large set of numbers and you try to squeeze them into a smaller set of numbers. There's many of them will map into the same kinds of numbers. Okay? And those are called collisions. Okay? So these collisions are basically, you have a couple of words. The example that they're giving is they have a couple of words. Here is demystify, and there's also melioration. I don't know what that means. What's melioration?
I think it's a form of demystifying.
Your guess is as good as mine. Okay? Okay? So there's different ways for you to do this. So one is basically fitting it where it's supposed to go. Okay, so one is open addressing. When a data item can be placed in the index calculated by the hash function, another location in the array is sought. Okay, searching through that array to find the correct spot to insert this thing is called probing. Okay, linear probing means we're going to start at the index where we're trying to insert this thing, and we're going to keep going one by one by one by one until we get to an empty spot, and then we're going to insert it there. Okay, and so that's the probe, and there's a picture in there basically, right? We're trying to insert where the 72 was, and we're going to keep going one down, one down, one down, one down until we find a place where we can insert this thing, and then we're going to finally insert it at index 57, and we're going to insert whatever we're trying to insert in there. Okay. However many steps you took to guess the empty spot where we can insert is known as your probe length. Okay? And the bunch of cells that are occupied, that are filling up the array that are being adjacent to each other and fill up the array is called a cluster. Okay? And yeah, I have some pictures in there. I'm going to go into too much detail on those. Okay, so this is your cluster, right? So you have a cluster of numbers. So this is an example of clustering. Okay, so the more your hash tables become clustered, the slower it becomes for you to insert into them. Okay, and by the way, what's the advantage of a hash table? The advantage is you're gonna have a data structure which is like a dictionary where you can just say, all right, the word is hippo, and it jumps straight to the place that is referring for a hippo. Okay, basically you can jump directly to the address without searching. So it's just like an array. You tell it go to index 999, hit, and it goes straight to that thing. So that's the advantage of having a dictionary. Okay. But that's not going to work too well when you're inserting things if you have these clusters. Okay? So one way to deal with this issue is you create quadratic probing. So what is a quadratic probing? I don't know if there's a picture. There you go. So what you're going to do is you're going to increment these probes, right? So the first time you try to insert something, you're going to try to go to the next one. The second time that you try to guess something, it's going to increase by a certain, predictable, step. right? So maybe the first time is 1, the second time is 2, the third time is 4, then it goes to 8, and it doubles up every time. And that eliminates somewhat some of these, clustering issues, okay? But not completely, okay? And then that's pretty much as far as I leave it here. But there is also other ways to insert into these hash tables. One way is if you try to insert into a cell that is already occupied, you could create a linked list at that spot, right? So let's say we're trying to insert where the 837 is. If it's already taken up, then you're going to create a separate linked list from that point on so that you can insert the next ones in that linked list. Another way is to change this quadratic probes, because every time you try to insert a new element, if that new element happens to be exactly where some other element was, and maybe you have tried to insert several of them already, right? So what's going to happen is you're still going to try to do the same quadratic probe for all these different elements that you're trying to insert into the same spots. So you're kind of running into the same kind of a clustering issue, right? You're going to build predictable clusters even if you have a quadratic probe. So then the next way to deal with this, other than the linked list that I mentioned, is to do this double hashing. And what is double hashing? Well, each individual key then is going to be hashed yet again a second time so that you can determine the size of your probe. So the size of the probe itself is going to depend on the number that you're trying to insert itself. Okay, so you're hashing the hash, and then that's going to get you, some totally random cluster, okay, or sets of clusters. Okay, and in the worst case scenario, you could have the whole thing filled up with clusters, and it just goes on into a never-ending loop, and then just loops and loops and loops forever, and you can never find an actual place to insert, your hash. Okay, so those are some of the issues and things. Yes.
So the insertion is a problem, could be a problem.
Mhm.
But in order to find your element, you have to know the algorithm that you used to
No. Well, in order to find the element, let's say I'm trying to find the Spanish word for 1. You just type 1 and it jumps straight to your
Right,
Spanish
but
word.
say that you had an issue inserting it in
Mhm.
the place. You had to use some algorithm to figure out where to insert it. Don't you need to know what that is to go find it?
Depending on, no, not necessarily.
How do you find it?
Using that same hashing algorithm that you do need to have that. Yeah, you do need to have an idea of what hashing algorithm you use to place it in order for you to retrieve it. Yes. Okay? Yes.
Can I have you scroll up, please?
Up.
Yes. I want to look higher. Yes, earlier, more.
Mm-hmm.
Continue, please. There was one of the sheets that I saw in here. If you're looking like in these listings, at some point it addresses the wraparound value. I wanted to know more about that wraparound condition.
Let's look at it in the office hour.
Okay.
Yeah, well, because we got another class. I'm hearing them. They're
Okay,
yeah.
no problem. Thanks.
Yep. So if you have any questions about this stuff, send me your emails. And just read the book. The as far as the hashing, I don't think it's terribly complicated. I kind of think the trees were a little bit more complicated than any of these other ones up to this point. But yeah, we'll talk over about this in the office hour, and then I'll probably post some extra things to explain people that same question. Okay. So that's basically what I have for you today. So I'll read chapter 11 of LaFour and the assignment. Let's see what do we have for us. Oh. Min and max heap. So yeah, that's not min and heap, max heap. I'm not sure why I'm putting heaps here and hashes. So I'll look at this thing. Trickle up, trickle down. Yeah, I don't know why I have 14. Yeah, for some reason I have a heap instead of a hash. Oh well, I'll look at it. Looks like I put the next week's assignment twice. Yeah, I messed up. I gotta re-update this assignment here. For some reason I put the same assignment twice, but I'll look at it and I'll fix it. Okay. Thanks to Canvas. All right, so that's it for today. Thanks for coming. Come to the office hour so that we can continue the conversation.